we're going to carry on looking at TLC, and we're going to look at what you do with the results. So you've carried out the experiment, you've followed the method through, and you've got this plate with these spots on, and you're going to measure this RF value, this retardation factor. It's going to be a fraction. Okay, so the number can never be bigger than 1 because the spot cannot move further than the solvent. So the first thing you need to do is get a ruler out onto your pack and measure the distance between where you spotted the sample and the solvent front. So how far is it from, so put your ruler on the bottom line and measure the distance to the top line. Doesn't matter what unit you measure in as long as you are consistent the whole way through. Now I measured this on an A4 version of the pack and it came to 53 millimeters. Even if you've used a smaller version of the picture, you'll get a smaller number here, but you'll get a comparable smaller number for the spots as well, and you should get the same RF values at the end. Then we're going to measure the distance for each one of these spots. So we're going to start at the centre of where we spotted them, and we're going to go to the middle. So if you put the ruler line on the middle of those, you can make sure that your line starts at the pencil line. Okay, measure each one of those. So I'm going to call my spots A, B, and C. Now, when I measured A, I got the distance to the spot as 43 millimeters. So what fraction of 53 millimeters is 43 millimeters? And I'm going to give it to 2 decimal places, 2 significant figures, because that's how much I've measured the distances to. And for B, so it's moved a lot less, it's a little bit more than half by the look of it, so I should get a number a little bit more than half. And for our final spot, it's moved probably about 1/3 of the way up the plate by looking at it with your eye. I'm getting 16 millimeters, oh not like 3. So why don't you have a look at this question and see if you can answer the question that's posed, which is which components are present in mixture M out of A, B, C and D, and how would you explain it, and then find the RF value and tell me which one has the strongest retention. So pause the video and see if you can answer that question. So we can look at it and we can say that the mixture M contains, if we have a look, mixture M contains spot A, spot C and spot D. Now you don't actually need to measure the RF values to be able to say they would have the same RF values, but that is the answer. It's not just they're at the same places. What do we mean by that in chemistry? We mean they have the same RF values. Then worked out the RF value of C. I've done it in millimeters. The fraction itself has no units, the final answer, because you divided millimeters by millimeters, just a fraction. And we can say that A had the strongest retention because it's gone the least distance, therefore it was the least soluble in the moving phase. Remember, it's a balance between solubility and retention, and if it's the least soluble, it's the most retained, and so that was our component with the strongest retention. The final thing to think about for TLC is what are some of the limitations? Well, some of the limitations are, if I was to look up, if I didn't know what my sample was, and look it up in a book of RF values, similar compounds, so 2 isomers of the same formula, will have similar RF values, and therefore you look them up in a book, it's very hard to tell which one you've got from this technique. So if they're very similar, they're going to have similar RF values. Unknown compounds have no reference data, so new things that you've discovered, you can look them up and they're not going to be there. So you can't figure out what it is. And the last thing is, it can often be difficult to find that combination of solvent and stationary phase that's going to separate all your components. Now there is a way that you can get around that a little bit. So perhaps you run your plate in a solvent and two spots come at the same place. That's another problem that we might have with this, that we see a bigger spot and it's actually two things in the same place. You can run something called two-dimensional chromatography, and we're going to look at that in our amino acids pack a bit later on. And what you do is you run it once and then you turn the plate 90 degrees and you run it again with a new solvent, and you get two RF values. That's going to increase your confidence in your identification. So that is how we carry out TLC and what we do with our results.